All right, I think we are now ready for the representatives from the Canadian Nuclear Safety Commission to make their presentation. Dr. Thompson.
Thank you, Madam Chair and members of the Commission. Mon nom est Patty Thompson. I'm the Director General of the Directorate of the Environmental and Radiation Protection and Assessment. With me today are Mr. Michael Rinker, the Director of the Environmental Risk Assessment Division, and Drs. Son Nguyen and Grant Su, who are two geoscience experts at the CNSC. Drs. Nguyen and Su have been leading the CNSC staff research and assessment work in the geoscientific fields related to the long-term safety case for the deep geologic repositories. In addition, Drs. Nguyen and Su, the CNSC has other geoscience experts in the fields of environmental engineering, structural geology, geomechanics, hydrology, hydrogeology, and biogeochemistry. Collectively, the CNSC geoscience experts have expertise in the above-mentioned fields as well as in the safety assessment of waste disposal. CNSC's geoscience experts all have PhDs either in science or engineering, and since 2009 have published over 20 research papers on topics related to this assessment in the peer-reviewed literature. Some staff are adjunct professors at Canadian universities, are invited as speakers at national and international scientific and technical conferences, or are active members and leaders in committees and working groups in international organizations such as the International Atomic Energy Agency and the Nuclear Energy Agency on issues related to the long-term safety of disposal in geologic formations. Their expertise is recognized by their peers, both nationally and internationally. The long-term safety case for the deep geologic repository is one of the most important parts of the review that was undertaken by CNSC staff for this project. A summary of CNSC staff's assessment for the long-term safety case for OPG's DGR project can be found in PMD 13 P1.3a. I will now ask Mr. Rinker to proceed with our presentation.
Good morning, Madam Chair, members of the Joint Review Panel. My name is Michael Rinker, and I'm the Director of the Environmental Risk Assessment Division at the CNSC. The purpose of this presentation is to provide CNSC staff's review and assessment of OPG's long-term safety case for the proposed Deep Geologic Repository project. We will present some key definitions and basic concepts and present the methodology used by the CNSC to assess OPG's long-term safety case. We will also present the results of CNSC's assessment, which includes an assessment of the geosphere where the repository is proposed to be located, the repository itself, evidence that supports long-term safety, and how uncertainties were dealt with in calculations of safety. Finally, we will present CNSC staff's conclusions for the long-term safety of the proposed project. The following definitions are taken from guidance documents from the International Atomic Energy Agency, the Nuclear Energy Agency, and the CNSC. They are accepted by the international community involved in setting requirements for the management of nuclear waste. Long-term safety is defined as the protection of people and the environment after closure of the repository. The safety assessment is a quantitative analysis of the level of protection provided by the repository system. The purpose is to bound the effects that the project may pose on the environment and to people and determine if certain acceptance criteria are met. A safety assessment is the usual type of assessment that would be conducted for any project in support of an environmental assessment. For this type of project, due to the long time frames, a safety assessment alone is not sufficient. It must be supported by multiple lines of reasoning and additional evidence. This is the purpose of a safety case. The safety case is a set of documents presenting multiple lines of evidence in support of long-term safety, and it includes a quantitative analysis or safety assessment. To add transparency, a long-term safety case requires identification of uncertainties, how the uncertainties are accounted for in the assessment, and future research activities that would be designed to minimize the uncertainty. In general, the purpose of the long-term safety case is to, first, support a regulatory decision to permit or not permit the continuation of the proposed EGR project. In particular, to inform a decision to proceed from one stage of the project to the other. And second, to identify uncertainties that need to be reduced by research, monitoring, or field verification. The long-term safety case is an important component, therefore, in the current environmental impact assessment and license application. The long-term safety case consists of three main lines of evidence. First, those related to the geosphere. Second, those related to the repository itself. And third, the evidence provided from the safety assessment. Overall, the evidence is used to provide confidence that the two main safety functions, containment and isolation, would be provided. These functions in turn provide long-term protection for people and the environment. Containment ensures that the wastes are contained in the repository and would only be released and migrate very slowly to the biosphere in harmless quantities. Isolation ensures that access to the waste is prevented, for example, by inadvertent intrusion or erosion. The typical phases in the development of a deep geologic repository are development of the concept or idea, finding a suitable site, constructing the facility, operating the facility, including the emplacement of waste, closing the facility, and post-closure, which includes monitoring to ensure that it performs as expected. The CNSC's regulatory oversight begins at the construction stage, which includes site preparation. International guidance recommends that the long-term safety case be developed at the initial stage of licensing. That is why the CNSC requires that a long-term safety case must be submitted for all stages of a repository development as part of a licensing application, and why it forms an essential part of the environmental assessment and licensing process. The safety case would also be periodically updated based on new information during the proposed life of the repository. The time frame for this assessment is 1 million years. This is a very long in comparison to human activity on Earth, but is relatively short compared to the geological history of the Michigan Basin, where the repository is proposed to be located. The upper timeline on this slide shows that sedimentary rocks of the Michigan Basin were deposited approximately 500 million years ago. Major tectonic processes ended about 250 million years ago after the Appalachian Mountains were formed. No major tectonic processes will occur for the next million years. In general, there is increased confidence in the results of a safety assessment when the geology is stable under the assessment period, and this is the case for the current project. Glaciation is the most important geologic process that would occur 1 million years into the future. This is shown in the enlargement at the lower part of the slide. There were approximately 9 glacial cycles in the past 1 million years. The cycles are expected to continue in the future with similar frequency. We are currently in an interglacial period. However, it is predicted that the next ice age would come approximately 60,000 years from now. CNSC staff have evaluated OPG safety case by using the following methodology, which is well aligned with international best practice. First, a pre-licensing review of key elements of the preliminary long-term safety case was conducted. Second, a review of OPG's safety case for the environmental assessment and license application was conducted by a comparison to Canadian and international guidance, a critical assessment of OPG's methodology and data, independent calculations, and seeking external advice on specific subject areas. The CNSC has also conducted independent research on topics such as natural tracers for determining the rate of movement of groundwater in and around the proposed repository, the impacts of glaciation on the repository, gas migration, and excavation damage zones. Information on these research activities can be found on the CNSC website at nuclearsafety.gc.ca. I will now present the results of CNSC staff assessment of OPG's long-term safety case. The first class of evidence relates to the geosphere. This figure provides a plan view of bedrock geology in southern Ontario and shows the location of the Bruce site, which is the proposed location of OPG's deep geologic repository. The DGR facility is proposed to be constructed in sedimentary rock of the Michigan Basin. The colors on this map indicate where certain rock formations outcrop on surface. The Great Lakes are shown in pale blue. The light green color corresponds to the Devonian Age sedimentary formation that outcrops on surface at the site of the proposed deep geologic repository. The DGR is proposed to be built at a depth of 680 meters within older Ordovician Age sedimentary rock, which is outcropping on the bright blue color on the map. The pink color is crystalline rock of the Canadian Shield, which underlines the sedimentary rock of the Michigan Basin. Pre-existing regional data and data from OPG's site characterization program confirmed the following favorable characteristics of the geosphere: low permeability of host rock and cap rocks. There is geological stability, including low seismic activity. There is geological predictability. There is geomechanical stability. The shallow groundwater resources are isolated, and there is low potential for natural resources. Details of the review of each of these attributes is provided in the following slides. Permeability is the property of rock to allow water to flow through it. When permeability is very low, contaminants move by diffusion. Diffusion being the movement of a solute in a fluid from an area of high concentration to an area of low concentration. Evidence for low permeability of both the host rock and the cap rock is based on the following. The permeabilities measured on the site are very low. It would take a water particle at the repository depth in undisturbed rock approximately 10 million years to move 1 meter. The values of diffusion coefficients measured from the laboratory and inferred from the natural tracer profiles at the site indicate that the rate of diffusion is very low. This attribute is important for containing the waste. Contaminants from the waste would move very slowly from the repository by the diffusion and not by the flow of water through the repository. For context, the geology of the proposed site exhibits equivalent or lower permeability and diffusion coefficients relative to geologic formations currently considered for geologic disposal of radioactive waste in other countries. The most convincing evidence for diffusion-dominated transport comes from the paleohydrogeological information. The natural tracer profiles of chloride, total dissolved solids, and oxygen isotopes show that the pore water in the host and cap formations is very old, likely in the order of hundreds of millions of years. The total dissolved solids profile shown on this slide illustrates 3 distinct groundwater regimes. First, the groundwater regime at the depth of the repository has very high total dissolved solids, indicative of brine, whose signature indicates a very ancient origin. Second, a shallow groundwater regime at up to approximately 200 meters depth. The chemical signature of this water indicates mixing with surface water, rainwater recharge, and glacial meltwaters. And third, an intermediate region in between the two. Calculations indicate that the establishment of these 3 groundwater regimes would take many millions of years. The calculations also suggest that the groundwater regimes evolved by diffusion-dominated transport processes in the host and the cap rock. Stability of the geosphere is important in support of containment and isolation and provides confidence in the safety assessment results. Evidence presented for geologic stability includes the following. The last active tectonic process was 250 million years ago. Second, the site is located in a seismically quiet area. Third, there is resilience to approximately 9 glacial cycles during the last 1 million years. CNSC staff conclude that the evidence supports geologic stability in the region of the proposed deep geologic repository. During the last 1 million years, the host and cap rocks have remained geologically stable under an estimated 9 glaciation cycles. Each cycle lasted approximately 120,000 years. During the last cycle, a continental ice cap up to 3 kilometers thick covered the site. The large load imposed by the ice cap produced a depression of the Earth's surface by hundreds of meters. The ice cap melted and retreated approximately 10,000 years ago, producing meltwaters that can infiltrate into the rock formations. Information, observations, and the results of the CNSC's independent research program on the effect of past glacial cycles show, however, that there is no water infiltration deeper than 200 meters. Permafrost penetration was restricted to the top 100 meters. No fracturing from the load imposed by the ice cap was induced at depths greater than 300 meters. This means that in the host and cap formations, solute transport remains diffusion dominated because new fractures were not created. The groundwater remains separated in 3 main zones as indicated earlier. A future glaciation cycle, similar to what occurred in the past, is expected to occur again at 60,000 years in the future. CNSC's independent research shows that the rock formations at the proposed depth of the repository would not be affected by future glaciation cycles. This also confirms OPG's findings. The ability to predict the stratigraphy at the site from regional borehole information provides confidence that the near horizontal layering of the geologic formations have not been offset by vertical faults. A 3-dimensional geologic model is the principal tool that was used to demonstrate the predictability in lateral continuity, depth, thickness, and configuration of the geological formations at the proposed site. The model incorporated information obtained from OPG drill holes, petroleum exploration, and development wells that existed previously, and from digitally available bedrock maps and reports. The stratigraphy documented from boreholes that were drilled after the model was developed is consistent with the model. This provides additional confidence on model accuracy and predictability of geological formations. There is no indication of large faults that would offset geological formations at the site scale, and the location of geologic formations at the site scale is therefore understood. Geomechanical stability is the ability of the rock mass to resist the effects of anticipated changes in stress conditions due to excavation, earthquakes, ice loading, and other external factors. Geomechanical stability ensures the containment function of the repository is maintained over time. The strength of the host rock is several times higher than that of sedimentary formations considered for geologic disposal of radioactive waste in other countries. Even with lower strength, the construction of stable galleries has been demonstrated in many underground research laboratories in Europe. The same rock formations as the host rock for the DGR are found at shallower depths in other locations in southern Ontario. The rock strength at these shallower depths is about 60% of the strength at the DGR site. In the past, underground engineered structures have been successfully excavated at Darlington, Wesleyville, and Niagara Falls. Based on that information, CNSC staff conclude that the repository could be constructed to first, provide a safe working environment, and second, reduce the extent of the excavation damage zone. The excavation damage zone will be discussed later as a repository attribute. The presence of natural resources could cause future explorers to drill into the waste. A qualitative assessment of natural resource potential has shown that the potential for resources in the area is low. Moreover, the repository depth minimizes the chances of inadvertent intrusion, particularly when there are no proven or expected resources. Nevertheless, the consequences of human intrusion, in which a borehole would be drilled through the repository, was conducted. The results from the safety assessment show that a future resident exposed as a result of this activity would receive a dose close to 1 millisievert per year. This is below background levels. Because of the very low probability of this event occurring and the dose consequences of the event being low, potential natural resource exploration in the area of the proposed project is not an impediment to safety of the project. For CNSC staff, this intrusion scenario compensates for the lack of a quantitative assessment of natural resource potential. I will continue to present the results of CNSC staff's assessment of OPG's long-term safety case, focusing on evidence relating to the repository itself. The most important attribute of the repository is its depth at 680 meters. Depth ensures that the waste is isolated from the biosphere. Depth is an important feature for the protection against future intrusion, and depth provides for many layers of low permeability rock above the waste. The following repository attributes support the containment function. First, a slow rate of gas migration. Second, the repository will likely not fully resaturate with water within 1 million years. Third, geomechanical damage from construction and future perturbations will not extend into the overlying shale cap rock. And fourth, the shaft will be sealed with chemically stable material. More details on staff evaluation of these attributes will be provided in the next few slides. Gas will be produced from the corrosion of metals and the decay of organic material that would be placed in the repository. OPG intends to leave the rooms and galleries open rather than backfilling the repository in order to allow space for the expansion of the generated gas. Therefore, the gas pressure will likely remain lower than the overburden pressure. This will minimize gas migration. The generated gas would contain radionuclides. However, the evidence from CNSC's independent research shows that the rate of gas migration is very slow, and this confirmed OPG's assertion that exposure to radionuclides from gas is not an overall concern for this project. Excavation of the shaft, the rooms, and the galleries of the repository would create damage in the rock due partly to the excavation methods, but mainly to the stress redistribution that would occur when rock is removed to create the repository. This excavation damage zone would have increased permeability compared to the initial undisturbed rock. The excavation damage zone could then be a preferential pathway for water and for gas flow. However, the excavation damage zone would not extend into the cap rock, and therefore contaminant migration would remain diffusion dominated. Evidence for this property includes the following. First, OPG's geomechanical model uses very conservative rock strength values and stress orientation. And second, CNSC staff performed independent calculations to verify this conclusion. This is illustrated in the figure, where the extent of the excavation damage zone around a typical emplacement room calculated by CNSC's model is shown in blue. The excavation damage zone remained within 4 meters of the roof of the room and with 7 meters from the floor. I will now discuss the results of the safety assessment. The safety assessment is based on an understanding of the repository system and its future evolution. Staff concludes the following. The safety assessment methodology follows Canadian and international guidance. The safety assessment was peer-reviewed by a team of international experts. The computer codes used are verified and validated. And fourth, the DGR system is robust and has addressed multiple scenarios. The scenarios used in the safety assessment were determined from an international database of likely and abnormal features, events, and processes. Scenarios are divided into two classes: normal evolution and disruptive scenarios. In the normal evolution scenario, a self-sufficient farming family is assumed to live directly above the main shaft. They are exposed to the potential release of contaminants through a variety of pathways. For example, ingestion of well water, gas flux from the shaft, and consumption of fish from the lake. For the normal evolution scenario, the maximum doses to the resident farming family and radiological and non-radiological impact on non-human biota are insignificant. That is, orders of magnitude below background levels of radiation and of the public dose limit. Four types of disruptive scenarios are considered: human intrusion, in which an exploration borehole is drilled through the repository and results in doses to the drill crew, the lab technician, nearby residents, and the resident farming family. Severe shaft failure, in which the shaft seals deteriorate, resulting in large increase in permeability of the shafts. A poorly sealed borehole, in which a site exploration or monitoring borehole is assumed to be poorly sealed. And a vertical fault scenario, in which an undetected vertical fault exists in the vicinity of the repository. The reactivated fault scenario results in insignificant dose when the fault is located 100 meters from the footprint of the repository. The poorly sealed borehole scenario also results in insignificant doses. The other two disruptive scenarios, shaft failure and intrusion, result in doses at approximately 1 millisievert per year, which is below background. Only one extreme variant of these scenarios results in doses of tens of millisieverts per year. The probability of this extreme variant is considered to be very low. Consequently, CNSC staff conclude that they result in acceptable risk. As recommended by international and CNSC guidance, a long-term safety case must identify uncertainties and how they are handled. This stems from the requirement that the safety case must be transparent. These uncertainties arise from the long time frame, the complexity of processes involved, and the natural variability of characteristics of the components of the repository. The uncertainties identified for this project have been considered and determined that they do not impact the conclusions of the current safety case. For transparency, CNSC staff will now discuss the main areas of uncertainty and how they were addressed in the assessment. OPG addressed the uncertainties that they identified in the assessment by using conservative assumptions, performing sensitivity analysis, and adopting bounding approaches. The conservative assumptions used to bound the uncertainties indicate that they do not compromise the safety of the proposed deep geologic repository. Staff identified 5 areas that require further attention, and these are discussed in the next 5 slides. The main component of the shaft seals are proposed to be constructed with a 70 to 30% by weight bentonite sand mixture. This type of material is chemically inert and is unlikely to degrade over time. However, it is noted that no full-scale precedent of a shaft seal using the same type of materials currently exist. OPG handled this uncertainty in the current assessment by considering a failed shaft scenario, which shows that humans and the environment would remain protected. If the project is approved to proceed, OPG would implement a quality assurance quality control program during the placement of the seals in order to achieve their target permeability. CNSC recommended in PMD 13-P1.3 that if the project goes ahead, OPG undertake an underground verification program and a research and development program in order to improve confidence in shaft seal performance. The site investigation performed by OPG did not detect the presence of subvertical faulting at and below the repository horizon. However, some uncertainty remains due to the limitation of geophysical methods from the surface and due to the relatively limited number of boreholes. OPG addressed this uncertainty by considering a disruptive scenario in the safety assessment where undetected faults at variable distances from the footprint of the DGR are assumed to exist. This scenario shows that the impact will be within acceptance criteria. OPG also commits to conduct geological mapping and extended geophysical investigations from deep underground during construction in order to verify the presence or absence of faults. This is also CNSC staff's recommendation. There are currently some sources of uncertainty related to the extent of the excavation damage zone. Due to, first, the lack of direct measurements of the in situ stress, which is the main cause of excavation damage zone. And second, the lack of specific experimental data on time-dependent mechanical properties of the host and cap rock formations. The above uncertainties were addressed in the assessment by using conservative long-term strength assumptions in calculating the excavation damage zone. In addition, during shaft excavation, OPG has committed to measure the in situ stress and characterize the excavation damage zone. Second, OPG would use controlled drill and blast excavation methods to minimize the excavation damage zone if the project is approved to proceed. OPG would confirm the geomechanical properties and how they would evolve over time. CNSC staff has provided a recommendation to the JRP on this topic. The uncertainties related to the waste characteristics come from the fact that only a few radionuclides, cesium-137, cobalt-60, are easily measured by gamma spectrometry. These are called easy-to-measure radionuclides. All other radionuclides are beta and alpha emitters and cannot be measured by gamma spectrometry. They are called difficult-to-measure radionuclides. Difficult-to-measure radionuclides were measured less frequently, but were also estimated using scaling factors. To handle this uncertainty, OPG has used the 95th% upper bound for iodine-129, which is the main contributor to dose in the safety assessment, to show that the dose is still insignificant for the normal evolution scenario, and the dose is in the order of 1 millisievert per annum for the failed shaft scenario. OPG has committed to improve their waste characterization program and to reduce this uncertainty before a license to operate would be granted. A CNSC staff recommendation deals with needed improvements to the waste characterization program. The corrosion of steel containers and degradation of organic material within these containers generates gas. The amount of gas produced would affect the pressure in the repository. The pressure in turn governs the rate of radioactive gas migration and also the rate of resaturation of the repository. There is uncertainty on that pressure due to the lack of real-world examples related to microbial activity responsible for waste degradation. OPG handled this uncertainty by using conservative assumptions related to the degradation rate or gas generation rate. The resulting dose remains order of magnitude below background levels of radiation. CNSC staff have recommended that OPG study gas generation processes in future should the project proceed. CNSC staff has reviewed OPG's long-term safety case and conducted independent research and calculations. Our conclusions are that, first, OPG's proposed project will not cause significant adverse environmental effects over the long term. Second, the long-term safety case is sufficient and acceptable. Third, the uncertainties associated with the long-term safety case have been managed in an acceptable manner. Fourth, a geoscience verification program would be conducted during site preparation and construction, with some aspects of this program continuing over time during operation. Fifth, CNSC staff are satisfied that the identified uncertainties can be reduced by the conduct of these verification and monitoring activities. I will now pass the presentation back to Dr. Thompson.
In conclusion, the multiple lines of evidence in the long-term safety case supports staff's conclusions that OPG's proposed DGR would not result in significant adverse impacts on the environment and human health. In other words, the uncertainties identified and explicitly addressed in the safety case do not equate to an uncertain conclusion. The characteristics of the geosphere support the conclusion that the proposed DGR on the Bruce site will not impact water quality in Lake Huron, even when disruptive scenarios are taken into consideration. And I would like to note that protection of Lake Huron, a concern that has been expressed by a large number of interveners, will be discussed further on September 30th and October 1st, and we have presentations on both of these days. I will also note that the radiological acceptance criteria for the long-term safety assessment will also be discussed in the staff's presentation on Friday, September 27th in the Human Health session. And we're available to answer your questions.